All right, so get this. We're diving into some serious AI stuff today.
Oh, yeah.
Yeah, it's cutting-edge research.
Cool.
And get this, it has the potential to, like, totally change things up.
Okay, I'm intrigued. Lay it on me.
We're talking linear recurrent neural network.
LRNNs?
Yeah, exactly.
I've been hearing a lot about those lately.
They're becoming, like, real contenders.
Oh, really?
Yeah, to those, like, super popular transformer models that everyone's talking about.
Interesting.
Especially when it comes to processing these huge amounts of data, like these long sequences.
Okay, so what's the big deal with LRNNs then? What makes them stand out?
Well, think about it. LRNNs like Mamba, RWKV, GLA, MLSTM, and DeltaNet.
Oh, okay, yeah, I've heard of some of those.
They're incredibly efficient.
Oh, that's cool. Efficiency is always good.
But there's this like mystery
Oh, mystery, yeah.
surrounding their ability to handle something called state tracking.
State tracking.
Yeah, it sounds pretty important.
Yeah, I mean, it sounds like it could be, but I'm not really sure what that means in, like, the AI world.
Well, imagine you're reading a book. To like understand the plot, you need to remember, or
Right, yeah.
gotta remember who the characters are.
Yeah, the relationship.
Their relationships, exactly, and all those events that have already happened.
Okay, so state tracking is kind of like remembering all that stuff for an AI.
That's basically it. It's like the AI's ability to keep track of the order
Okay.
and the connections between, all those pieces in a sequence.
Ah.
So it could be words in a sentence,
Uh-huh.
or musical notes,
Oh, okay, I get it.
or even moves in a chess game.
Ah, that makes a lot of sense.
It's like remembering the past to understand the present, basically.
So if an AI can't do that, if it can't track state,
It's going to make mistakes.
yeah, obviously,
Yeah, because it's missing those crucial pieces of information.
that's a big problem.
It is. And that's what LRNNs have been struggling with.
So how do we fix that?
Well, the research we're looking at today tackles this head on. They're investigating the role of something called eigenvalues.
Begging what?
Eigenvalues. It's like they found a hidden control panel.
A hidden control panel.
Yeah, inside these networks.
That could unlock a whole new level of capability.
Exactly.
I mean, I remember Eigenvalues vaguely, like from way back when in some math class I took, but
Yeah, me too.
what are they exactly, and like why are they so important for these LRNNs?
Okay, think of a matrix.
Like a grid of numbers.
Yeah, like a grid of numbers.
Okay.
It's like a blueprint.
For transforming information.
That you got it. Now, eigenvalues are these special numbers.
Okay.
They're associated with a matrix.
Uh-huh.
They tell you how much that matrix stretches or shrinks a vector.
A vector.
Yeah, think of it like an arrow,
Oh, okay.
pointing in a specific direction.
Okay, I can visualize that.
When you apply the matrix to that vector.
So they're kind of like scaling factors,
Yeah.
right? They tell you how much something gets like magnified or compressed.
That's a perfect way to put it.
Okay, cool. I'm starting to get it.
Now, when it comes to LRNNs,
Yeah.
these matrices, they're used to update the network's state. So it's internal memory
Right.
as it's processing information over time.
Makes sense.
And those eigenvalues,
Yeah.
they play a crucial role.
In how the LRNN remembers.
Yeah. Or
So-
forgets information.
So if you adjust to those eigenvalues.
You can basically fine-tune how the LRNN handles its memory.
Wow. That's pretty powerful stuff.
It is. And here's the thing. What researchers have found
Yeah.
is that most current LRNNs,
Uh-huh.
they limit their eigenvalues.
Limit them.
Yeah, to a range between 0 and 1.
Interesting.
And this restriction
Yeah.
might be what's holding them back.
From effectively tracking state information.
Precisely.
So it's like they've been working with only a limited set of tools this whole time, and
Yeah.
now they're like, wait a minute, there's a whole toolbox out there.
That's a great analogy. And what this research explores
Yeah.
is the possibility of expanding that toolbox
Okay, how do they do that?
by extending the eigenvalue range
Oh,
to include negative values.
negative values.
Yeah.
That sounds kind of counterintuitive.
We know, right?
What does that even mean for the network?
It's like giving the LRNN a whole new set of moves.
Okay.
By incorporating those negative eigenvalues,
Yeah.
we allow the network to not just remember information,
Uh-huh.
but also to selectively forget it
Selectively forget.
or dampen certain parts of its memory.
Oh, so it's not just about storing everything, it's about remembering the right things.
You got it.
That makes sense.
But how do they actually do this?
Well, the researchers focused on two specific types of LRNNs.
Okay.
Those with diagonal and those with generalized household or state transition matrices.
Matrices again. Are we going full-on math class here?
No, we'll keep it high level.
Okay, good.
Just think of these matrices as like different configurations of that control panel.
Oh, okay, that makes sense.
Yeah, they determine how the network manipulates the information.
As it flows through the system.
Exactly.
Okay, great.
So they looked at these different types of LRNNs.
Yeah.
And then what? What did they change?
They introduced a modification.
Okay.
It essentially adjusts the settings on that control panel.
Interesting.
They call it a bias term.
A bias term.
It's small,
Uh-huh.
but it's a strategic addition.
To the equation.
Yeah, that governs how the network updates its state.
So by adding this bias term
They can shift the range of possible eigenvalues.
to include those negative values.
Exactly.
Clever. But did it actually work? In practice?
Well, to see how much of a difference this change really makes,
Okay.
we need to start with a puzzle.
A puzzle.
Yeah, one that's historically stumped these LRNNs.
Okay. What kind of puzzle?
It's called the parity problem.
The parity problem. All right. I'm listening.
So imagine you have a sequence of ones and zeros.
Okay, 10, 1001.
Yeah, exactly like that.
All right.
The parity problem is simply figuring out
Okay.
if that string has an odd or even number of ones.
That's it.
That's it.
That's easy. For us.
Right. It's just basic counting.
Exactly.
But for traditional LRNNs,
Yeah.
it's been a surprisingly tough one to solve.
Really?
Yeah, they consistently fail
Huh.
because they struggle to maintain that necessary information.
About the past inputs, right?
Exactly, to make the correct judgment.
So nonlinear RNNs, like LSTMs.
Yeah, they handle it fine.
But LRNNs have been falling short.
That's the problem.
And that's where this research comes in.
You got it. So are you telling me
Yeah.
that by incorporating these negative eigenvalues,
They actually managed to get LRNNs to solve this parity problem?
that's exactly what they found?
Well, that's pretty cool.
The modified LRNNs with that expanded eigenvalue range
Yeah.
could now effectively track the state information.
That was needed to, determine the parity of a sequence.
It's a pretty big deal. It shows that this small tweak
Yeah,
can have a significant impact on what LRNNs can do.
totally. But solving this parity problem is just one piece of the puzzle, right? What other tests did they run?
They didn't stop there.
Okay, good.
They tested these modified LRNNs
Uh-huh.
on a range of tasks.
Designed to assess
Yeah, their state tracking abilities.
more complex scenarios.
Exactly. We're talking Chomsky hierarchy tasks
Okay.
and state tracking experiment.
Which involve?
Understanding different levels of grammatical complexity
Uh-huh.
and following abstract rules.
Okay, break those down for me. I need a little more explanation on what exactly those tasks are and what they tell us.
That's a great question, and that's where we'll pick up in the next part of our deep dive.
Perfect. I'm looking forward to it.
We'll explore those specific challenges
Okay.
and how these modified LRNNs performed,
Sounds good.
and what those results really tell us about their potential for real-world applications.
I'm ready when you are.
Let's do it.
Awesome.
Great.
Cool.
I'm excited for this.
So remember those experiments we were talking about?
Yeah, the ones testing those modified LRNNs
Right.
to see if they can handle more complex scenarios.
Exactly. We got to push them beyond those simple tasks.
Like that parity problem, as cool as it was.
Yeah, we want to know if they can actually be useful in real-world application.
Right, exactly.
So they started with these things called
Great.
Chomsky hierarchy tasks.
Chomsky hierarchy tasks.
Okay.
That sounds
No, it sounds a little intimidating.
a little bit.
But it's all about understanding
Yeah.
how LRNNs handle different types of languages
Okay.
with different levels of complexity.
So it's like testing the LRNN's language skills,
Yeah.
but in a more structured way.
You got it. It's like a standardized test.
Okay.
The Chomsky hierarchy.
Yep.
It categorizes languages based on their grammatical rules.
So like some languages are easier to learn than others.
Exactly. You've got those regular languages.
Okay.
They're pretty straightforward.
Okay.
And then you've got context-free languages.
Mm-hmm.
Those are more complex
Okay.
because the model has to keep track of all
Yeah.
these intricate relationships.
Between the words. So did the modified LRNNs,
Yeah.
did they do any better on these language tasks than the standard models?
Okay, so what they found was pretty remarkable.
Oh, really?
Yeah, those modified LRNNs,
Mhm.
especially the ones with the expanded eigenvalue range, remember?
Right, with those negative values.
They consistently outperformed the traditional ones
Okay.
on those tasks involving context-free languages.
Wow, so incorporating those negative eigenvalues actually helped the LRNNs, understand more complex grammar.
That's what it looks like.
Huh.
It suggests that
Yeah.
that expanded eigenvalue range is giving them more tools.
Oh, like more tools to work with.
Yeah, to manipulate their memory.
So they can keep track of all those dependencies and relationships that make those complex languages work.
Makes sense, right?
It does, yeah.
Yeah.
But, okay, that's starting to show how these abstract mathematical tweaks,
Right.
can translate into real benefits.
Yeah.
But what about tasks that are more directly relevant to the real world?
Okay, yeah, that's a good point.
Did they test the LRNNs on anything like that?
They did.
Okay, good. Tell me more.
They did a bunch of state tracking experiments focusing on
Yeah.
what are called group word problems.
Group word problems. Okay, what are those?
I know, they might sound a bit obscure,
Yeah.
but they're actually really interesting. They're
Yeah.
all about understanding
Okay.
how actions or like operations
Yeah.
combine and interact within a specific set of rules.
So it's like testing if the LRNN can think logically
Exactly. Like, can it reason?
and follow instructions.
Yeah, exactly.
Okay.
So think of it like this.
Okay.
You've got a set of objects
Okay.
and a set of rules for combining them.
Right.
The LRNN has to figure out what happens in the end
Okay.
based on a sequence of actions.
Applied to those objects. All right, I'm following.
It's testing whether the model can, like, maintain an accurate picture
Of what's going on
of the state of those objects.
as they're being, manipulated.
Right, exactly.
Okay, that sounds like a good test for state tracking.
It is. It really is.
So how did they do?
Okay, so this is where it gets even more interesting.
Oh, really?
Yeah, the researchers found that the modified LRNNs, once again, they showed some big improvements
Okay.
over those traditional counterparts.
So they were better at solving these group word problems.
They were way better.
Ah.
It shows that they had an enhanced capacity for logical reasoning
Okay.
and state tracking.
That's impressive. It really seems like these negative eigenvalues are like a key
Yeah.
to unlock a whole new level of performance for these LRNNs.
I know, right? It's pretty cool.
It is. But I have to ask,
Okay.
how do these abstract tasks,
Yeah.
like language parsing and group word problems,
Right.
how does that help, someone who's not a linguist or a mathematician?
Okay, that's the crucial question.
Yeah.
And that's where things get really exciting.
Okay, I'm listening.
These abstract tasks are actually quite relevant
Oh.
to a wide range of real-world applications.
All right, give me some examples. I'm ready.
One area
Yeah.
where enhanced state tracking could make a huge difference
Okay.
is natural language understanding
Okay.
and generation.
Uh-huh.
Imagine AI assistants
Yeah.
that can actually follow a conversation,
Oh,
remember past interactions,
that'd be amazing.
and respond in a way
Yeah.
that's truly contextually relevant.
That would be a game changer. I mean, we've all had those frustrating experiences
Right, exactly.
when you're trying to talk to a chatbot
Yeah.
and it just feels
It's
like,
just spitting out canned responses.
yeah, it's not really understanding what you're saying.
Exactly.
So with improved state tracking,
LRNNs could potentially power
and,
AI systems that are way better
and understanding language,
than understanding the nuances of human language.
leading to better communication.
More natural and effective communication.
That would be incredibly useful
Wow.
in so many areas.
Think about it.
Customer service, education, healthcare.
Healthcare, entertainment even.
Exactly. All sorts of stuff.
But what about beyond language?
Okay, good question.
Are there other areas where this enhanced state tracking could have an impact?
Absolutely. Anything that involves
Yeah.
analyzing and predicting sequences of events.
Like, give me an example.
Financial forecasting
Okay.
relies heavily on understanding
Huh?
the relationships between past events
Yeah.
and future outcomes.
So these modified LRNNs could potentially lead to better financial predictions.
That's definitely a possibility.
Wow.
And it's not just finance.
Oh,
Any domain
Yeah.
that involves processing time series data.
So like weather patterns.
Yeah, weather patterns, traffic flow, medical records even.
Wow.
That could
From AI models that can track and analyze those complex sequences of events.
That's right.
This is incredible. It sounds like we're talking about a huge shift
I know, right?
in what AI can actually do.
Yeah.
And it's all thanks to this, like, subtle tweak. This one little tweak.
To these things called eigenvalues.
Exactly.
It's amazing how powerful
Yeah.
fundamental research can be.
It is. Sometimes it's these small adjustments that unlock a whole new level of capability.
It's crazy.
It really is.
It's exciting to think about all these applications.
Yeah, the possibilities are endless.
But, I also wonder
Yeah.
about the potential downsides.
Right. There's always two sides to the coin.
Are there any risks
Yeah.
or challenges with developing AI models
Yeah.
that are this powerful?
That's a really important question.
Yeah.
And it's one that we need to address
Yeah.
carefully as we move forward.
Because more powerful AI doesn't automatically mean a better world, right?
Exactly.
We need to be thoughtful.
We need to think about how these advancements are developed and used.
Yeah. What are some of your concerns?
Okay, so one concern is bias.
Bias.
The potential for bias to be
Yeah.
amplified
Uh-huh.
if these AI models are trained on data that reflects existing societal biases.
Right. So if we're not careful,
Yeah,
we could end up with systems that perpetuate those inequalities.
exactly.
That's a crucial point, you know?
It is.
It's not enough to just make these models more capable.
Right.
We also need to make sure they're being used ethically.
Yeah, fairly and ethically.
Okay.
That's a good point. What else?
Another concern
Yeah.
is the potential impact
Oh,
on the job market.
oh yeah, jobs.
As AI systems get more sophisticated,
Uh-huh.
they could potentially automate
Yeah.
tasks that are currently being done by humans,
Right.
leading to job displacement.
Yeah, that's a real concern,
It is.
and it's something that we need to be thinking about.
We need to figure out
Yeah.
how we can prepare our workforce for the future.
For an AI-driven world,
Exactly.
it's not just about developing the technology. It's
Right.
about making sure that
Yeah.
the benefits are shared.
With everyone.
Yeah, broadly.
And that we minimize any negative consequences. It sounds like there's a lot of responsibility
There is.
on the shoulders of the researchers
Yeah, and the developers.
who are creating these AI systems.
Absolutely. They have a big responsibility.
Yeah, they do.
And that's why we need to have these conversations
Open and transparent conversations.
about the potential impact of AI.
And get everyone involved.
Reverse perspectives, policymakers, industry leaders, the public.
It's a good point.
It's not just a technological advancement,
Yeah.
it's a societal one.
We need to make sure AI is developed and used in a way that aligns with our values.
Exactly. That's a great way to put it.
This deep dive has been quite a ride.
I know, right?
We started with this small tweak,
To Eigenvalues.
Yeah.
These little things.
and we ended up talking about the future of AI and its impact on the world.
It's amazing.
It's incredible how even the most technical stuff can have such a big impact.
It really shows how interconnected everything is.
It does.
Important to stay informed.
Yeah, even if you're not a scientist or a mathematician.
Everyone should understand the basics.
Everyone.
And be aware of the potential benefits and risks.
Because AI is becoming more and more a part of our lives.
It's true. It's everywhere.
It's everywhere, yes.
So it's crucial for everyone to participate in the conversations.
That are shaping its future.
Absolutely.
That's what we aim to do here on the Deep Dive.
That's right.
To empower you with the knowledge and insights to navigate this complex world.
The world of AI, it's a wild ride.
It is a rapidly evolving world.
I know, right? It seems like every day there's something new.
And I think we've accomplished that today.
I think so too.
We delved into the fascinating world of LRNNs.
Yeah, those negative eigenvalues.
Yeah,
And what it all means for our future.
it's been a real pleasure having you here.
The pleasure was all mine. Thanks for having me.
And to all of you listening out there.
Keep learning, keep asking questions.
Yeah, stay curious.
Absolutely.
Let's shape the future of AI together.
I love that.
Until next time, this is the Deep Dive signing off. Okay, so we've seen how these negative eigenvalues can supercharge those LRNNs.
Yeah, their state tracking abilities are way better.
But what does that actually mean for AI, in the long run?
That's the big question, isn't it?
How is this going to affect our world?
And it's not an easy one to answer.
Yeah, I bet.
On the one hand,
Yeah.
we have this incredible potential for positive change.
Give me some examples.
Imagine AI systems that can actually understand us.
Really understand us.
Yeah, and respond to our needs.
Okay, I like where this is going.
Like personalized education
Okay.
that adapts to how we learn best.
Oh, that's cool.
Or medical diagnoses that take into account our whole health history.
That would be amazing.
Right.
AI could actually help us solve those complex problems
Exactly.
and improve our lives in so many ways.
It's exciting to think about.
It is,
Yeah.
but like with any powerful technology,
We always risk.
right? More powerful AI doesn't automatically mean a better world.
That's for sure.
We have to be careful about how these advancements are developed and used.
Absolutely.
So what are some of the things that worry you?
Well, one thing is bias.
Bias.
Yeah, if these AI models are trained on data that already has bias in it,
Okay, I see.
we could end up with systems that just make those inequalities worse.
That's a really good point. We don't want that.
We really don't.
It's not enough to just make AI more powerful. We have to make sure it's being used fairly.
Ethically.
Ethically,
Yeah.
yeah.
That's super important.
What else worries you?
Another concern is jobs.
Jobs.
Yeah, the job market.
Oh, right.
As AI becomes more sophisticated,
Uh-huh.
it could start doing jobs that humans are doing now.
And people would lose their jobs.
Yeah, job displacement is a real concern.
We need to be ready for that.
Absolutely.
We need to prepare people for the future of work, in this AI-driven world.
We have to think about that now.
It's a big responsibility.
It is.
For the people who are creating these systems.
The researchers, the developers, they have a big role to play.
We need to talk about this more.
We need to have open conversations about the potential impact.
Everyone needs to be involved.
Researchers, policymakers, industry leaders.
The public.
It's not just about the technology.
It's about society.
Exactly.
We need to shape AI in a way that aligns with our values as a society.
I completely agree.
Wow, this deep dive has been amazing.
It has, right.
We started with these tiny eigenvalues.
The little tweaks.
And now we're talking about the future of AI and its impact on the world.
It's wild how these technical things can have such big consequences.
It really shows how everything is connected.
It does. It's fascinating.
We need to stay informed and engaged, even if we're not scientists or mathematicians,
It's crucial for everyone to understand the basics.
because AI is everywhere.
It's becoming more and more integrated into our lives every day.
That's why we do the deep dive.
To give you the knowledge and insights you need to navigate this crazy world,
The world of AI.
it's changing so fast.
And I think we've done that today.
I think so too.
We learned about RNNs, those negative eigenvalues.
And what it all means for the future.
It's been fantastic having you here.
Thanks for having me. It's been a pleasure.
And to everyone listening out there, stay curious.
Keep exploring.
And let's shape the future of AI together.
I love it.
Until next time, this is The Deep Dive, signing off.